I'm recording this, good. Loops in R are relatively slow, so it is best to avoid loops. Luckily enough, that is quite easy because we can use R's vectorized nature and subsetting tricks to avoid loops in many circumstances. We'll start with a very simple example. Suppose I want to calculate the sum of two vectors. And I'll just fill two vectors x and y now with white noise. And I put 1,000,000 entries in x and I put 1,000,000 entries in y. And now suppose all I want to do is calculate the sum of x plus y. Now R is vectorized, so I can simply set z to be x plus y. And if I want to find out how long it takes to perform that operation, I just put system.time around it. And that tells me how long this takes. And you will see that is virtually instantaneous. It took 2 milliseconds. Now I could do the same using a loop, and that will be a lot slower. So let's look at it. So if I want to do this using a loop, I'll just open one set of curly brackets, and then I have to set the vector z to be a numeric vector which is of the same length as x. I then have a loop, so I do for I in sequence along, now they're all of the same length, so suppose I sequence along x. And now zi to be xi plus yi. I close my curly brackets and close my round brackets, and I get the same results from this command as I got from setting z here to the sum of x plus y, but the price I pay for using a loop is essentially it's about 400 times slower than using R's vectorized nature. Now I can actually do worse than that. I can, for example, instead of creating a vector z of the correct size, create a vector z that is empty and then simply append another element. So I can do that by, I want to measure again how long it takes, and now I simply create z to be an empty vector. I leave the rest of the statements just as they are, and let's see how long that takes. Now that is actually a valid statement. So what this does is it starts with z to be an empty vector. So when R tries to set the first element, it realizes, oh, I don't have a first element. So it extends the vector z to be of length 1. Then R tries to set the second element in z, and again it can't find the second element, and then it extends the vector z to length 2, and so on and so forth. And as you can see, this is a very slow process. So we're still waiting for the results to be calculated. R is taking quite a while. So actually, rather than waiting, I can explain to you why it's taking that long. The reason why it's taking so long is that we start off with an empty vector z. Now that empty vector z cannot hold an entry. So if you want to set the first entry of z, what R needs to do is find some other space in memory that's big enough for one entry, get rid of the old z, and that lets us now store, say, the first entry. Suppose that's a 5. Now I want to set the second entry of z. Now again, z isn't big enough that I can set a second entry, and there might be something else stored in memory right after z. So what I need to do is copy z over into a location where I have actually space for another entry. So I have to copy over z. So now I have copied over z so I can forget about the old value. And now I have space for another entry, say -1. Now if I want to set now the third entry of z, again, I can't just stick it there. That bit of memory might be used for something else. So what I need to do is copy again. So copy the entry to somewhere in the memory where I have space for 3 entries. So I now copy over 5 and minus 1. Now R can forget about the old value of Z, and I can now set the last entry to say 3. Now if I want to set the 4th entry, I need to copy over the vector again, and so on and so forth. So actually, this is very expensive. It's not the setting of the entry that is expensive, it's the copying. Because if I set the ith entry, I have to copy I minus 1 entries over. So essentially, if I set 1,000,000 values in the vector Z, I am copying 1,000,000 times the vector Z. And this takes a long time. You can see, we still don't have results, and I must have waited by now for at least 5 minutes. So let's wait till we've got a result. And finally, we have a result after almost 1,000 seconds. So if you extend the vector one by one, it takes 1,000 times as long than if you create a vector of the same length. So even though the fact that R can extend the vector for you if needed is useful, using it incurs a massive performance penalty. And of course, if we compare it to the time it would take if we had just calculated x plus y, that's off now by a factor of almost 1,000,000. Avoiding loops is a bit of an art, so I'll present one more example of how we can turn a loop into a vectorized statement. This is a slightly more complicated example where we are trying to compute the increments in a vector x. So suppose my vector x has the entries 3, 5, 9, 7, 4. Then the vector of increments is, well, the first increment is x2 minus x1. So I have to add 2 to get here. Then getting from 5 to 9, I need to add 4. Or in other words, 9 minus 5 is 4. To get from 9 to 7, I need to add minus 2. And to get from 7 to 4, I subtract minus 3. So my vector d of increments is of length 4. That's 1 less than the vector x. And the numbers are given in the second column here. And they're just calculated by taking xi plus 1 minus xi. So in a loop, I can do this as follows. I can set n to the length of x. I create now the vector d, which is length n minus 1. And then I'm going along the entries of d, setting them to be xi plus 1 minus xi. I made sure I've set d to the correct length to avoid having the performance problems we had before when we extended a vector in the loop. So how can we avoid a loop? The loop is comparing xi plus 1 minus xi. So I can't just define d to be x minus x. That wouldn't work. So how can I actually make this work? Let's look at it. Let's start off with just copying down x again. So that is 3, 5, 9, 7, and 4. And what I'll do is I'll copy down, so this is my x. I'll copy down x again, but offset by 1. 3, 5, 9, 7, and 4. And now you can see that the first entry of d was 5 minus 3. So 5 minus 3 is 2. The second entry of d is 9 minus 5. 9 minus 5 was 4. The third entry of d was minus 2 because that was 7 minus 9. 7 minus 9 is minus 2. 4 minus 7 is minus 3. 4 minus 7 is minus 3. So I have managed to actually calculate d by subtracting x from x, but by offsetting it a little. Now let's ignore the offsetting. So what I'll do is I'll erase that 3 here, and I'll erase the 4 here. So what do I have here? Well, here I have the vector 5, 9, 7, 4. 5, 9, 7, 4. That's all the entries of x except for the first one. So that's x without the first entry. And here I've got 3, 5, 9, 7. 3, 5, 9, 7. That's all the entries of x except for the last one. So I can indeed calculate d by just taking x without the first element minus x without the nth element. And with that trick, I actually have a vectorized way of calculating d. So this is now our R code. We set n to the length of x, and then we simply set d to be x without the first element minus x without the last element. And this runs in just 48 milliseconds.